Hi everyone, and as promised, I'm continuing with using a computer instead of my writing. And here I am in a simple Python notebook, and the first thing I did was just kind of load in that example we were using. I'm not going to do anything fancy with it, it's just going to help me do some basic counting. So there's that data that we looked at before. And here's that Shannon entropy formula, and what I did was create just a simple Python formula that implements this formula. And let me just load that. And progressing down in the simple tasks we're doing. So here is that first thing we did where we looked at looking at who was home, and 4 times it was empty that we looked. Once Anne was there alone, once Sarah was there alone, and twice both people were there. So let's just check my formula to see if it's correct. So that would be info. And then I just put in those numbers, 4, 1, 1, 2. And that's what we came up with before. It takes on average 1.75 bits to encode this task. And keep in mind, it's just the probabilities, not the raw numbers. So if I had 40 occurrences of that the house was empty, 10 where Anne was there, 10 where Sarah was there, and 20 times both were there, it's the same number of bits, right? So it's just the probabilities, not the raw numbers. All right, so now let's look at that mountain biking example. So scrolling up here, remember that we started with just counting the bike column just to get the rough idea of, without doing any questions, what the entropy was. And if we counted these, there were 5 no's and 9 yeses. So we can get the entropy of the problem just to start with. Now let's do that. So it's 5 occurrences of not mountain biking, I think, and 9 mountain biking. And that's the entropy. And when we did it by hand, we got the same entropy. All right, now the question is, can we ask some question related to one of those columns and reduce this entropy? And so can we reduce it? And we're going to look at which column reduces it more, and that'll be the first question we're going to ask. So let's examine what the entropy is after we ask the question of what's the outlook. And here I just got my little table here of when it's sunny, what it looks like, so I can do some easy counting. And here we see there were 3 no's and 2 yeses. So let's put that in. So when it's sunny, that value is info 3, 2. Let me just print sunny just so we see what it is. 9, 7. And overcast, here we see the overcast examples. Every time it's overcast, this person mountain bikes. Sweet. So let's just get that entropy. We know what it is. It's the same as the cat example, but might as well just do it just for completeness. Okay. It's a little error in my program. That's not going to affect anything, but I get -0 there. And let's take a look when it's raining. There's the raining examples, and you see 3 times when it rained, the person mountain biked, and twice that person did not. So let's get that in. Yep. All right, so now we've computed entropy as it says here for each of the 3 conditions. And we want, though, the entropy for the entire question, not just what's the entropy when it's sunny, but what's the entropy after we ask the question, what's the outlook? And for that, we need to know kind of the percentages in each of these cases. How many sunnies were there, how many overcast, and how many were rain. And I counted those right as we see right there, that 5 of them were sunny, 4 were overcast, and 5 were rain. So we're going to weight each of these based on how many occurrences there were in each category, the category of sunny, overcast, and rain. And here's how we're going to do that. So I'll just call it outlook. And since 5 of the 14, were sunny, I'm just going to do that. So 5/14 of the answer is going to be the sunny case. And 4 of them were overcast, so 4 out of 14 were the overcast condition. And then 5 were the rain condition. Yep. All right. So that's my entropy for the entire question of outlook, or the entire column. So initially the entropy was what? I think it was 0.9. Let's go zooming up here. 0.9402. And now it's 0.6, wherever that is. 0.6935. So that's a pretty good reduction in entropy, right? So we're able to encode the problem after we ask outlook with fewer bits. So it's much better to ask what outlook is than ask no question at all. That's probably not surprising. But maybe temperature is a better question to ask initially. So let's try that approach. So let's try hot. And that's the hot condition where there were 2 no's and 2 yeses. And you probably know the entropy of that already, right? So it's the same as a coin toss. It's a kind of a 50-50 proposition. But let's stick it in. So it takes 1 bit to encode that. And mild is here, where we have 6 of them. And 4 times when it was mild, the person mountain biked. Let's do that. And I should point out before I get too far along that we're not going to be doing this. I mean, I'm just showing you by hand how things work. And once we are constructing decision trees, it's going to be a lot easier than this. I'm just trying to help you understand how a decision tree works, how we construct a decision tree. So don't panic that we have to do this long, by hand involved stuff. It's instantaneous when we really use it. All right, and now let's look at cool. So there's 4 cools, and 3 times when it was cool, the person mountain biked. Okay, and we got the entropy there. And now we have to compute the entropy for the entire temperature case. So that is temp. And remember, we have to portion the value based on how many there were. So how many were there for hot? So for that, I have to go back up and actually look. I think there were 4, but let me check. Yep, there were 4 instances of hot. And there were 6 of mild. And there were 4 of cool. Whoop. Oh, I missed the multiplication symbol. So temperature was, the entropy of that whole question was 0.91. So if I had to choose between temperature and outlook, outlook was, I think, something like 0.69. That's a much better question to ask initially than, hey, what's the temperature? But there's a few more we can check. So let's check humidity. So here I just list all of them. And the person didn't mountain bike 1, 2, 3, 4 times. And they did mountain bike 1, 2, 3 times. So it's 4 and 3 with high humidity, or high humidity. And when humidity is normal, that's the chart we got. There's 7 of them, I guess. 1, 2, 3, 4, 5, 6, 7. Yes. And 1, 2, 3, 5, 6 times when it was normal, the person mountain biked. Cool. Okay, and now let's check the humidity. Get the entire value. So it was 7 14ths times what is called high. Yes. 7884. So far still the outlook's the best question to ask since it was 0.69, but humidity is better than temperature. So now the final one is, what about wind? Maybe wind would be good. So here's the cases where wind is strong. 1, 2, 3 occurrences of no, and 3 occurrences of yes. And when it's weak, here's the case. So we have 1, 2, 3, 4, 5, 6 yeses and 1, 2 no's. So let's get the weak done. Weak wind. 6, 2. We get that. And finally, now we compute the entropy for the entire column. And that was 6 14s times strong plus so we get wind here being 8921. So again, the original entropy before we did anything was 0.9403. And here's the entropy for each column or each question. So outlook was 0.6935, temperature 0.9111, humidity 0.7885, and wind 0.8921. So the best initial question here to ask is outlook. So the first question we're going to ask is, hey, what's the outlook? Now let's say, suppose after we ask that question, the person says sunny. Now the question is, after they say sunny, what's the question we should ask? So should we ask about temperature, humidity, or wind? So let's do that data. So let's say we ask about temperature. So let's do this. So we'll say hot equals, now I have to do some counting. Whoops. So when it's hot, there were 2 cases of that and they both were no. So it's just info 2. Mild. Equals, there were 2 cases there. And once the person biked and once the person didn't bike. I got that kind of reversed, but it's the same. And then finally cool. There was only 1, I think, right? 1, and they biked. Doesn't matter, I guess. So now we get the whole for the column. So that would be temp. And we're only looking at when the condition is sunny because the person told us sunny. We said, hey, what's the outlook? Person said sunny. Now we have to figure out, well, what is the next logical question to ask? That's where we're at in this. So temperature equals, there were 2/5 of them were this hot category plus 2/5 were the mild category plus 1/5 were the cool category. And finally, let's just see what that is. So that's 0.4. That looks pretty good. We reduced the entropy there by asking that question. Let's check with humidity. So I'm looking up here again. We have 3 with high humidity, and when the humidity is high, the person doesn't mountain bike. Or, when the humidity is high, yeah, that's right. The person doesn't mountain bike. All right, so let's do that. High equals info 3. Let's just print out what that is. that's 0. And when it's normal humidity, the person mountain bikes. Well, it's going to be the same. It's going to be 0. So the entropy there is 0. As soon as we ask, hey, what's the humidity? If they say hi, we say you didn't mountain bike. And if they said it's normal, we'll say they did mountain bike. So we don't need to really go any further here. So we've kind of investigated that the next best question to ask after we ask what's outlook and they say sunny, we would say, hey, what's the humidity? Let's just back up a bit, and let's say in response to the what is the outlook, the person responds overcast. That's here. And again, we don't have to go any further because every time they said overcast, they biked. So this is what it looks like so far, that the first question we ask is what's the outlook? If they say sunny, we computed the next best question to ask is, hey, the next question to ask is what's the humidity? And we don't need to ask any further questions because it's perfect. As soon as they say hi, we know they didn't do it, they didn't bike, and if they said it's normal, we know that the person biked. For outlook here, if they said overcast, 100% of the time they say overcast, we know they biked, so we can say yes here. And the thing we didn't finish is, well, what happens if they said it rained? What to do then? And I'm not going to do that because I think we have a pretty good understanding of how all this works. So that's kind of the theory behind decision trees, right? So we're computing entropy, and based on this drop of entropy, the best question to ask is going to be the question with that results in the lowest entropy. So that's it for here. The next thing we're going to look at is, well, how do we implement this with scikit-learn? How does it actually work when we run that algorithm? And that's what we'll explore next.